Hello, it's James Black. I'm one of the instructors for the EMEC 361 Measurements and Instrumentation Lab here at Montana State University. It's spring 2020. We're right in the middle of the coronavirus pandemic/panic. We're all online for all of our classes, including this lab. So I'm doing the lab for you. I'm creating a video of this. I'm going to have a few exercises or a few tasks I want you to do from the data I collect here. The big picture is that we're using ultrasound for non-destructive testing. I'll bring you in closer so you can see this equipment better, but again, the big picture is we have this pulse echo unit. It transmits and receives ultrasound, so it uses a piezoelectric transducer. It sends it, it receives it. So we're just going from a coax into the unit. I have a sink and the signal coming out the back, and we're running these into an oscilloscope. I have the sink in channel 1 because by default this will trigger on channel 1. We'll get a more stable image that way. And then I have my signal coming into channel 2. So what you would normally be doing in the first part of this lab is you would get a specimen like this. It's this aluminum block. It has a wood block on the back side to cover up a shape that has been machined inside. And you would need to use ultrasound to find the shape of this. You would create a grid on here. You'd start with a bigger grid, and then when you found roughly where that area was, you would refine your grid and come in to get that shape in more detail. And you wouldn't be allowed to open this up to see what that shape is until the end. Since I'm over here and I have one in my hand, I'll show you that transducer. So this is what it looks like. You might not be able to see this. There's a 10 and a 0.25 written on there. The 10 would stand for 10 megahertz. That would be a higher frequency transducer. That would be better for these smaller samples in terms of the depth. Say 1 inch might be a good rule of thumb to say. If it's less than 1 inch, this would be good for that. The 0.25, that's the 0.25 inch diameter of this transducer. So that, we're going to use a lower frequency transducer that is bigger for the second part where we're dealing with a bigger sample. That will work better for that. Another advantage of this smaller one is that when you're trying to go over this grid, you get better spatial resolution with a smaller transducer. If you're ever doing this, make sure you pull off the red cap. I see a lot of students will think that's like a grip and use the back side of it, and that doesn't work. This side without the writing, that's what you want to put down onto what you're trying to measure. We're also going to have to use some couplant between our transducer and our specimen. For this part, we'll be using glycerin. So here we're going to be measuring longitudinal. We're measuring longitudinal waves. We want to get the velocity. What happens is when you put this on here, even though you're putting it very close, tight to it, there are still discontinuities. And the basis of ultrasound is that when it sees a discontinuity in density, that a big change like that is an acoustic impedance, and it reflects the sound back. So if we use glycerin, we get rid of the small air pockets between our transducer and what we're trying to measure. it'll give us a better signal. We'll use an adhesive when we go to the shear wave speed, but that'll be part 2. For right now, we're just using glycerin. That's probably enough of the big picture. I'm going to bring you in a little closer here so you can see the equipment better. I ended up bringing the oscilloscope down here onto the workbench so you'd get a better view. We have everything in one frame. Just turning everything on. Give that a second to warm up. Like I said, I'm running the sync into channel 1, my signal into channel 2. The oscilloscope by default will trigger to channel 1, and by having the sync there, we're going to get a more stable image. I'll show you what happens if, so the trigger on channel 2, there, see, it's all jumping all over the place. Just get a better image, a more stable image when it triggers to sync, and by putting on that L1, save a few seconds if you were just doing this to actually measure something, not as a demo. So this is already looking fairly good. Let's zoom in a little bit. Yeah, actually, one thing before I zoom in, so we have a lot of controls on this transmit receiver unit. I wanted to show you so we have this one here, PRF. This is pulse repetition frequency. And if you see here, so we have these series of pulses that it's sending out. So adjusting this will adjust the frequency, or the amount of time between each of those pulses. See there. So in this case, where we're measuring something under an inch, we could just have this at the max. Some other settings on here are the damping. We have a pulse height high, a gain, either the full or a minus 20 dB cut on it, and we have a gain setting here too. Most of that stuff we'll just keep on max. I guess the pulse height's on high, the gain is on full. Our gain is on 6 out of 10 right now. That should work well. The damping is on high. We can adjust those a little bit when we zoom in to see. The one last setting I wanted to show on here was this mode switch. So here we're connected to this coax that says T/R. So the T is for transmit, R is for receive. And when we're in this position up here, you see the little transducer with an arrow that goes up and down, and it's sitting on what you would be measuring. So when you're in this setting and you're plugged into here, you have a transducer that is transmitting and receiving. You could, as an option, have one actuator, it'd be a transducer, on this side, and it would only transmit, and then you could have another one on this side for only receiving. And when you flip this down, you would switch to that. But we're using one transducer for transmitting and receiving. Now let's do the zooming in. Make sure you have a good image of that. There's again a little bit of glare. Let's see. There, got rid of that glare. Now so we have our sync channel 1 in yellow, we have our signal down here on channel 2 in blue. Let's move that channel 2 up. We might want to, so we can align these for now. You might want to separate them, but let's align them, And then let's zoom in a little. Yeah, that's still okay. Maybe we want to get shrink our trigger a little and get that out of the way for now, at least. And then channel 2. So that's pretty good. I think we're zoomed in pretty well for vertical. Let's do the horizontal now. So let's just zoom in. Here, this might help if I put this on here. So I'm putting the transducer onto what we're measuring, and there you just saw a bunch of reflections appear. So that sound keeps going through. It gets reflected back when it reaches each side of it. We see multiple reflections for each pulse. So let's try to keep my hands out of the way here for you. Let's zoom in there and move things over this way. So there, we're seeing some pretty good. We see our pulse, we see all the echoes. It's all pretty clear. This is pretty good right now. We could, so look here, I have the sample. I have some glycerin here. Maybe I could use a little more glycerin. We don't want to put a lot on, but we want to make sure we get a good signal. So you can spread that around a little bit. So that looks good. And see, right now we are, right now we are over a place of known thickness, right? There's nothing machined into the backside of that there. So we can measure that thickness. I have this caliper here to do that with, and we can measure the time it takes. Now remember, it's going to be the time it takes to go through and come back. So time it takes to go through and come back. We can get that thickness here, and we can get the time it takes here. So from that, you're going to be able to determine the speed of sound. And this is aluminum. You can go online, something like Engineer's Toolbox, find a speed of sound for aluminum for longitudinal wave speed, and compare it. Make sure that we're in the ballpark. And then we're going to use that speed of sound to find the depth of the part that's been machined out. So let's do that here. So let me get a good signal again. We're over the part that is of a known thickness that we can measure. There's no wood on the backside. There's nothing machined out of it. We have these pulses here. Let's use the cursor. So my cursor is off right now. I want vertical bars, right? So vertical bars, I'll be able to measure the time between these echoes. So let me move one. We just move it to one spot in that echo, and then we want to move the next one. So we select that, and then we move the other one to roughly the same part on the next echo. So that was the time to go through and come back. Let's turn the menu off here. We'll see it over here. So the change in time was 3.04 microseconds. That's one bit of information you're going to need to use. So 3.04 microseconds. Now let's get the thickness of this using this caliper. So we'll come in here. We're at, let's call it point. Oh, wait a second. Oops, it slipped. 0.388. See that point? 0.388 inches. So 3.04 microseconds, 0.388 inches. Now you need to calculate that, find a longitudinal speed of sound through aluminum, and compare it. Make sure we're in the ballpark. When we're in the ballpark, we're going to then take that speed of sound for whatever this type of aluminum is here that we have, and well, normally in lab you would start, let me see that you're still in the frame here. Let's move over here. So you would start to move this around, and you're seeing there that the time between echoes isn't really changing. So we must currently, oh, there's maybe something, oh, so that was something. We moved over an area where it's machined. So you would start with like a big grid, you'd move around, you move all over the place. And so here where it hasn't been machined, and then we move over to where it has been machined. So like I showed you with this one, there's just going to be two different depths. Since you can't actually do this and go over and find where that machined out part begins and ends, all I'm going to have you do here is, based on the time that we're about to measure, determine the depth of what's been machined out. This isn't EMEC 103. It doesn't do me any good to give you a drawing of where stuff is and have you reproduce the drawing and tell me back where I told you stuff was. So we're not going to do that. Normally you would produce a drawing of what you determined using ultrasound. This case, you're just going to find the depth. So let's get that time that you need for that. Okay, here we are over a section of that. Maybe it'd help if we zoomed in a little bit on this. It's a little... The pulses are a little quicker together. You know, it takes less time for it to go through and come back, right? So we have it lined up so that one cursor is on the leading edge of that, and then on this echo back, we are now on the leading edge, and the change in time between those is 1.76 microseconds. Right up here. So using that 1.76 microseconds and the speed of sound through this sample that you calculated, I want you to tell me what the depth of that part that's been machined out is. That's it for part A. I'm going to do a little switch out here and we'll do part B soon. Peekaboo. I was just messing with you there a little bit. Go stir crazy a little when you're being locked up from coronavirus. Anyways, we're back, and I'm not even gonna try to be in the frame here, just causing problems. So in part B, what we're gonna be doing is, we have this brass sample, and we are going to be measuring the longitudinal wave speed through it and the shear wave speed through it. And I'm telling you it's brass so you can compare your findings to something online. But what we're trying to do here is to determine the material properties of our sample based on measuring these two different wave speeds. As we covered in lecture, longitudinal wave, so both of these waves are going to propagate in a direction normal to the face of our transducer. The longitudinal waves are going to be oscillating, so we're going to have our compressions and our rarefactions. We're going to get those oscillations in a direction parallel to the propagation of the sound wave. The shear wave, it's also going to propagate. So both of these are going to be propagating. If we have the transducer like this, they're going to be propagating down through the sample and coming back up. Like we said, the longitudinal one is going to be oscillating in this direction. It's like you took a slinky and you compressed it, pulled it back, compressed it, pulled it back. And the shear transducer, so we need to use a different type of transducer for this. The shear transducer, the sound will also be propagating in that same direction, but the oscillations of the sound pressure, the sound wave is going to be oscillating in a direction perpendicular to that direction of propagation. So here we have, like we did before, we have a number that says the frequency, so it's 2.25 megahertz. Probably can't see that, but that's what that is. And then we have 0.5, so 0.5 inch diameter. This is larger than, we gave that 1 inch as kind of a rule of thumb. Here we're not trying to find anything in kind of horizontal pattern, so we don't need the spatial resolution. It's a little bit thicker sample, so these larger transducers would be a better choice. It has a model number on here, V106, so Panametrics, which is Olympus, V106. This one, if you went and looked it up, you'd find this is for longitudinal waves. Then this one, everything's the same except for there's a different, it all appears to be the same, but there's a different model number, V154. If you look that up, you'd find that it's for shear waves or transverse waves. Just to kind of speed this up and help us to separate them faster, we've etched a little S in there for shear. So we know this one is for shear, this one is for longitudinal. We're going to measure each of these separately. So let's start with the longitudinal. This will be much like what we did in part A. Still measuring longitudinal sound waves. So let's just use a little glycerin. And I haven't adjusted this at all. Maybe we should pull back our pulse repetition frequency a little bit. We don't see any change right here. If we zoomed out to see more of the pulses, we would see them move further apart. The greater thickness, it might help to have that frequency, that repetition frequency reduced. But so here I've put, am I not, what's happening? I'm not seeing anything. Oh, there it is, okay. So I zoomed out. Let's move this over this way. I zoom out, we probably should see even more of them. So it's definitely not as strong here. Let's zoom back in. It looks, what we see, so we see our initial, then we see an echo, we see another echo here, and then it's basically already at the point of where it's not rising above the noise floor right there. But whoops, I don't want to zoom in or zoom out anymore. I was trying to move it over a little. Let's zoom back into, this is all we need right here. So we can measure the time between those. I thought you might be interested in, so here we have it sitting on wood. What's the difference if we raise it up? There's not really any difference. We're still, mostly those changes in amplitude are from me moving this transducer around. So obviously brass is much more dense than the wood. So we're still having this change in density. We're still having this acoustic impedance change. So we are getting the reflection same amount of time. Let's go and measure that. So we want to bring back, oh actually we have our cursor on there. So let's bring one cursor to front edge of this. Select that. Let's bring the other one to the front edge of this one. And our change in time is 17.9 microseconds. Right up there. So that's one important piece of information you're going to need. Now let's do the same thing for the data we need for the shear wave speed. And I'm going to wipe this glycerin off, and I'm going to change out this transducer for the shear. And now, instead of using glycerin, we're going to use this Olympus couplant SWC-2. I'm actually not exactly sure what this is made of. I know it's water soluble, so you can just clean it up with water, and it's an adhesive. So here, because those oscillations are perpendicular to the propagation path, we need to have something that is going to make that connection, to make those perpendicular oscillations transmit into the specimen. So there, we don't need a whole lot of that. Put some on there, and we'll put this on and get a nice good connection on there. So see, it's adhesive, it's sticking to it. Now let's find our, so out there. Let's turn our gain up. Probably could have done that before. So turn the gain up. Oops. So there we're seeing a couple echoes. Let's use our cursor again. So we'll set one right there this time. Select, we'll set another right there. Let's turn these menus off so it kind of cleans up our view. And this time it is 36.2 microseconds. 36.2 microseconds. Time it takes to go through and come back for shear sound waves. So obviously, because those are different times, you're going to have, and it's the same distance, you're going to have different speeds for those two waves. Let's get the thickness through there. That's the last bit of information you'll need. You'll need the density too. You can just get that from some reliable site online. Whoops, I'm going to need more water to clean that up. But we'll measure it back here. Oops. This caliper is getting old. We are at, you see that? We're at 1.506 inches. Whoops, it slipped. It was 1.506 inches. So using the equations that you were given in lab, calculate Poisson's ratio, Young's modulus, and the shear modulus. There'll be some more information about how you are supposed to submit that. It will come along with the links to these videos. That's all for now. Stay healthy.